The first important statistical piece of information we're going to talk about is expectation. Actually, it's something you know already, but it wasn't called expectation. So x is our discrete random variable. The expected value is the answer we would expect to get. Had to roll a dice, what would you expect to get when you rolled it? By the way, does anyone know what you expect to get when you roll a dice? I think it's 3.5, but anyway. So the expected value of x is, there's our formula, the sum of the probability of x times the x value itself. The sum of all of those will give us the expected value. So what is this little px? Well, that's what I'm saying. It's the probability of x equals x, and a reminder, that's always greater than or equal to 0. Another note to make there, I said you know about it already, it's actually average. Right? Expected value of x turns out to be the average of a set of data. Or more correctly to call it the arithmetic mean. And that's why sometimes we use the word mean instead of average. Expected value of x is a measure of central tendency. You might remember that term from your junior stats. Central tendency is talking about where is the middle of the data. And the average is one of the ways we do that. I'm sure you could tell me another way. What's another measure of central tendency? Median. That, in fact, will give you the exact middle of the data. And there's a third one we often use, mode, which I think is a terrible way of measuring the centre because it's, why does it have to be in the middle? But anyway. Okay, so here are some rules, some laws of expectation. If a and b are constant, then the expected value of a times x plus b would in fact be the same as a times the expected value of x plus b. Here's the proof. Okay, using our formula, the expected value of ax plus b would be the sum of ax plus b times the probability of x. It's a sum, and because there's a plus in there, I can break that up into two separate sums. So it would be the sum of axpx plus the sum of bpx. But remember, a and b are constants. So every number inside these sums are multiplied by a or multiplied by b, which means we could factorise it out of the sum. So I'll get a times the sum of xpx plus b times the sum of px. Well, hang on. B is a constant number. And the probability of x, the sum of the probability of x, must be 1. We said they all add up to 1. So that's just b. Here, xpx, well, that's what we just defined to be ex. So we do end up with a times ex plus b. Second one, expected value of x plus y would be the same as the expected value of x plus the expected value of y. All right, let's have a look at this example. 25 families have been polled to fend for the number of litres of milk consumed during a particular week. Based on this data, how many litres of milk would you expect a similar family to consume in a week? You see, this is what we do with stats. We go and do research. So we can make generalisations, and that allows, in something like this, it might allow marketing teams to work out where best to place their ads and things like that. Okay, let's draw up the table. I've put in two rows here because in order to find the expected value of x, I'm going to need xpx. So first thing I do is write down the probability of x. Well, that's simple enough because we know there's 25. I've just got to put each of those numbers over 25, and indeed they do add up to 1. So the next row, I just multiply each of those by x. So 0, 5 on 25, and so on. It adds up to be 2.2. So therefore we know the expected value of x is 2.2, or another way of saying that is the average is 2.2. Why is expected value the same as the average? Because if you don't know, and you say, well, what would you expect to get? Well, you would expect to get the average. That's a logical sort of assumption to make. Of course, another way you could have done it, if you really wanted to, you could say, oh, I know expected value is the same as the average. So we add them all up and divide by the number of terms we've got. So, well, I've got 2 lots of zeros, 5 lots of 1s, 9 lots of 2s, and so on, divided by 25, and surprise, surprise, you get 2.2 as well. I'm not suggesting you do it that way, by the way. Random variables have an expected value. Sample spaces have a mean. So that is the technical difference between expected value and mean. When we're talking about random variables, we say we have an expected value. Whereas when we're just talking about a sample space of data, we say, well, that has a mean or that has an average. But essentially they're the same thing.